Alright, we are on podcast 3.1. This is a new unit of forces. We're going to talk about Isaac's 3 laws of motion, which introduce us to forces. So, let's proceed. Let's start off by defining what a force is. A force is any push or pull put upon one object by another object. So I've got 2 examples here. One, we have a rocket. Let's blow that up a little bit. And another, we have actually a person who is showing, I actually found this on a chiropractic website, someone who's using proper form to lift a box. Now notice, there are forces in play here. And here's a key clue there. There's an arrow. Something is moving up. Okay, so this person is putting a force upon the box that's lifting it up. It doesn't have to be a lifting it, though. It could just be this. Well, I guess you can consider what's working against this box, and we can talk about force of gravity. All right, so you often hear in documentaries of forces of nature, and forces of nature don't include things like, the hurricanes and tornadoes and stampeding elephants. They do include we're going to list off 2, but there's 4 true forces of nature. One is the force of gravity. Okay, and so that is one. You can see that this person here is lifting up a box against the force of gravity. So that box is pretty heavy, it looks like, and you got to use proper lifting techniques, but we write that as F sub G. We also have, I'm going to make my pen a little thicker, we have the force of magnetism, which you are all aware of, and that's these 2 magnets attracting, or a magnet attracting another magnet, or a refrigerator attracting a little knick-knack from the thrift store that holds up a piece of paper. These are pulling each other towards one another. There are some forces that have little to do with gravity or magnetism. We call these mechanical forces when they're forces of motion. And these require energy, which is something that we have not yet quite introduced. But if I am going to pedal a bicycle, I've got to press down, and I've got to use the energy in my legs and the energy in my cells in order to do that. And so this, if I'm going to drive a truck, I've got to put gas in that truck, and I've got to apply it and use that energy to apply the force. So these are examples of mechanical forces. So Isaac Newton gets a lot of credit for these forces. He came up with the law of gravity, which basically says that all objects are attracted to other objects. And this did not come from an apple falling onto his head. Yes, an apple did fall. Actually, he watched the apples fall. It didn't fall on his head. That's a fable. But when he was a child, that was something that fascinated him, and he continued to pursue it. And he came up with this law of gravity. But he also came up with the first, second, and third laws of motion, which really are still used today. NASA uses these because they're spot on accurate. So with each of these laws, I'm going to take a definition or 2. Actually, I have 2 definitions. One from Wikipedia, one from a website called the Physics Classroom. And let's just use these 2 and let's kind of analyze them. So this is Wikipedia right here. If an object experiences no net force, so there's no forces acting upon it, then its velocity is constant. So if it's at rest, it's going to stay at rest. Or if it's moving, it's going to move in a straight line with constant speed. So the velocity will be the same, and the acceleration will be 0. Newton's first law of motion is often stated as an object at rest stays at rest, and an object in motion stays in motion. Unless it's acted upon by an unbalanced force. So he keeps talking about these no net forces and these unbalanced forces acted upon by an object. So let's make an object. I would like to have a blue circle with a red outline. And this, let's just let it sit there. Boom, it's resting. So an object at rest stays at rest unless acted upon by an unbalanced force. Unbalanced force means we're just going to move it and have the force acting in one direction or another. So where's my arrow button? Okay, so boom, there's a force, and we're going to click this ball, and that ball's going to start moving. And it's not going to move away from this line. It's going to same speed, same direction, same velocity up until we hit. Let's make a little brick wall here with one brick, and let's take this and whoops. Okay, we'll just put it right in front. All right, let's start the ball again. It's moving, and it hits the ball, and it hits the wall, and it stops. Okay, so there's your unbalanced force. So this force is acting in the opposite direction of the motion. So that actually looks like, well, can I spin this? No, I can't. All right, so I was going to say it's in the opposite direction. Let's see if I can do that again. No. I'm just going to keep making these. No. All right. All right, we have two more definitions for Newton's second law. Wikipedia says the acceleration, or the A, of the body is parallel and directly proportional to the net force of the body. And it's in direction of the net force and inversely proportional to the mass of the body. So the equation they give us is F equals ma. Or, the acceleration of an object produced by a net force is directly proportional to the magnitude of the net force. So we're talking about acceleration again, and it's in the same direction, which means it's a velocity, as the net force, and inversely proportional to the mass of the force, mass of the object. So what are we saying here? Let's get our blue ball back. So I have a ball, okay? And let's take another ball, and let's actually make it twice the mass. Oh, I gotta click the ball button. Okay, so ball A has a mass of x, and ball B has a mass of 2x, and they're not proportional, obviously. And then let's try to push them with the same force. Okay, so we're going to make two force arrows here. Okay, and one more. And they have to be the same. Okay. So, my force is the same. My mass actually let's take this ball and get rid of it. And let's make a big red ball. So use this big red ball and we'll get rid of the blue ball. Alright. So, remember we talked about how a force is a push or a pull, but that means that we are changing the motion. We are accelerating that object. So we have a blue ball that has a mass, and we have a red ball that has twice that mass. So what's going to happen to the acceleration? Well, you guys know the answer to this already. If I'm pushing this blue ball with this force, and I'm pushing the red ball with the same force, this ball that has a mass that is less will accelerate twice as much. And this ball that has a mass of twice will accelerate half as much as the blue ball. All right. So apply this to, say you're pushing a wagon, one with one child in it and another with 5 children. It's more difficult to push the mass, or the wagon with the more mass. Okay, and so that's all Newton's second law is saying, is that we have an inverse proportion of mass to acceleration. So if the if the force is the same and you push something with a greater mass, you're going to get less acceleration. But if you push something with a smaller mass, you get more acceleration. So for Newton's third law, I like the physics classroom definition better. For every action, there's an equal and opposite reaction. So we can look at this one. It says, when the first body exerts a force on the second body, blah, blah, blah. But let's look at the rocket again. The rocket is applying a force. And it's the gas that's coming out of these jets, and it's applying a force downward. But what's happening in the motion? The motion is actually moving upward. So our first action is right here. The equal and opposite reaction occurs right here. Now, when you are on a skateboard, let's see if I can draw a skateboard. Okay, skateboard. Okay, if I'm pushing and I'm trying to go in this direction, which way do I have to push off? That way. Okay. So, skateboard is going to the left, okay, but I have to push it to the right. Equal and opposite reaction. I'm done. Period 7. Thanks for helping me out. Everybody say goodbye.